This is a screencast to review 2's complement numbers. So I've written out a 5-bit set of binary numbers here, starting at the bottom down here with 0 and moving all the way up to the value 31 at the top, which is 1, 1, 1, 1, 1. If we treat them as unsigned numbers, these are the numeric values associated with each binary value. Over here on the right, I've written out the negative number that would be associated with those same bits if we are considering them as a 2's complement number. The difference between a normal unsigned binary value and a 2's complement value is that in 2's complement representation, we treat the most significant bit, that is the leftmost bit when we write it out, as a negative value instead of a positive value. So for example, if I look here, the value that is 22 as a positive number, or as an unsigned value, is negative 10 as a 2's complement number. Because we have this first bit, which is worth negative 16, then we add the 4 and a 2, and when you add 4 and 2 to negative 16, you get negative 10. So whereas in an unsigned representation, if we start at 0 and count all the way up, just incrementing the bits, we go from 0 to 31. In a 2's complement representation, this wraps around once the most significant bit becomes a 1. So we have the values 0 through 15, and then we have negative 16 up to negative 1. And another way to illustrate this would be to just move these. So I'm going to delete those rows and paste them back at the top. And now we have, we're back to having the smallest value at the bottom and the largest value at the top, this time counting from negative 16 up to negative 1, then 0 up through 15. Now in either case, working with unsigned values or working with 2's complement signed values, there is a way to write the numbers out so that you have a continuous spread of values from the smallest possible value up to the largest possible value. And then there's going to be a discontinuity there where you wrap around from the largest possible value you can represent to the smallest value. We could represent this by drawing a circle. I can't do that easily in my editor, so I won't do it here, but it's sometimes helpful to look at things that way. So the largest and smallest values that we can represent also are different for unsigned values and 2's complement numbers. In the case of a 2's complement number, the largest value we can represent is a 0 in the first bit, since it would have a negative value, and then all of the other bits set to 1. In this case, it's 15. The smallest possible value we can represent is that 1 in the first bit, since it represents a large negative value, and then zeros everywhere else, since those ones in those positions would just push it back closer to 0. This also means that negative 1 is represented by all 1s. It's negative, so we have the first bit set to pull it down in the negative direction, but then we have all the other bits set to pull it back up to being as close to 0 as possible. Negative 2 is the same, but the last bit is clear. So that's negative 16 plus 8 gives us negative 8, plus 4 gives us negative 4, plus 2 gives us negative 2. Note that when we add together 8 plus 4 plus 2 plus 1, that only gives us 15, not quite enough to counter the negative 16 that the first bit gives us, that first value that first bit gives us. So in a 2's complement representation, there are a few things to recognize. One is that the first bit is enough to tell you if the number is positive or negative. So if the first bit is a 1, then that means this is going to be a negative value. That negative 16 is going to be enough to overpower any other contributions from the other bits. A 0 in the front means it's a positive number, or technically a non-negative number, because 0 is represented with a 0 at the beginning, and 0 is neither positive nor negative. Note also that the range of values is neatly split between the negative values and the non-negative values. We have exactly half of them are negative numbers, negative 1 through negative 16, and half of them are non-negative numbers, 0 through 15. We do have one more negative number than we do positive number. The range goes to negative 16, but it only goes up to positive 15. Now, why is this representation useful? Mainly because arithmetic works the same for 2's complement numbers as it does for unsigned values. So note that, let's start with -1. -1 is represented using the same bit pattern that 31 would be in an unsigned representation. If you add -1 to some other value, let's say we add it to 4, if we were just to add those bits, we would get something that exceeds the largest possible 5-bit value we can represent, and so it has to wrap around. So if we take 4 and add -1 to it, we actually get 3 because we count all the way up. So note that -1 is the same as 31, so I'm just going to count here. We go from 4, if we add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we wrap around, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31, we end up at 3. So -1 is represented by a very large unsigned value, large enough that it almost wraps all the way around to back where we started. It goes all the way around -1. Similarly, -3, if we were to add that to a value, we would count all the way around a complete circle -3. We're 3 short of adding a complete wraparound to these values. We could also kind of think of 0 as representing -0. If we had an extra bit, we could get that to look like a 32, and it would be enough to add it all the way to circle completely around. There's also, note that no matter how many bits we have, if they're all 1, we're going to have -1. And this gives us an operation we call sign extension. If we want to extend a 5-bit number into, say, a 7-bit number, I could just add 2 1s in front of it, and I'd have the same numeric value. That is to say, I take the first bit, and I just copy that to the left as many times as necessary to extend this from, in this case, a 5-bit representation to however many bits we want to extend to. And let's just take a look at what's happening. So here, as I said, we have -16 plus 8 plus 4 plus 2 plus 1. So if we were to add 1 extra bit to this, making it so it had 6 1s instead of 5, think about what happens in the representation. That value under the cursor right now that was a -16 before becomes a +16. So instead of subtracting 16 from the value, it adds 16 to the value. Or in other words, adding that bit in front is basically added 32 to this. We went from -16 to +16. But we also added a new bit whose value is -32. So by making this 5th bit from a negative value to a positive value, we effectively add 32 to the number, and then we subtract that 32 right back off by adding the bit in front. If we were to add another one, then this bit under the cursor, which was -32, becomes +32, so we basically add 64 to the number, but the extra bit in front is now a -64. One more time, we end up, this -64 becomes +164, adding 128 to the value, but we add a -128 to the front, and so the value cancels out. So in this case, we have -128 plus 64 is -64, plus 32 is -32, plus 16 is -16, plus 8 is -8, plus 4 is -4, plus 2 is -2, plus 1 is -1. So no matter how many bits we have, if they're all 1s, it's going to represent -1. The most negative value we can do is always going to be a 1 followed by a bunch of zeros, because that captures all the negative value without adding any positive to it. The positive numbers are exactly the same as the unsigned values, so there's less to say about those. It's also useful to be able to convert between 2's complement and a decimal representation. There are a couple ways to do this. One, if you have the bits of a 2's complement number and you want to convert that to a negative number or a positive number, we'll kind of neglect the positive numbers here because, again, they're the same as the unsigned values. But if we want to convert a negative number that we have in 2's complement to its decimal equivalent, we have a couple approaches we can take. One is to just add up the values of the bits. So like here, this value 10011, we know that the most significant bit is worth negative 16. So we just add that with this bit, which is a 2, and this bit, which is a 1. So negative 16 plus 2 plus 1 is negative 13. So we can do it directly. Another thing we can do is convert it into a positive number. So we negate the value and then convert that into a decimal number. So let's take that same value of 19. So I'm just going to write it down here, 10011. To convert a negative value to a positive value, or a positive value to a negative value, we flip all of the bits, and then we add 1. So I flipped all the bits, and if I add 1 to it, I get this number. And if we convert that to base 10, we have an 8 plus a 4 plus a 1. That's 8 plus 4 is 12, plus 1 is 13. So our original value was negative 13. Note that it's equivalent to subtract 1 first, and then flip the bits. Gives us the same result. So to convert between positive and negative values, we simply flip the bits and add 1, or subtract 1 and then flip the bits. Either approach will yield the same result.